Dear friends, this lecture is devoted to one more widely used method for material science investigation. I'm talking about scanning electron microscopy. Indeed, if you remember, we outlined 3 different levels of material structure, so including atomic, crystalline, and microstructure. We talked with you about a couple of methods which are used in order to investigate atomic structure. I'm talking about transmission electron microscopy, and crystal structure. I'm talking about X-ray diffraction analysis. So today we will talk about methods which is widely used in order to investigate microstructure, scanning electron microscopy. So this screen again reminds you about the different level of material structure and their scales. And now we are talking about scales on the order of microns, while you will see later that the advanced current microscopes, scanning electron microscopes, do have resolution close to 1 nanometer. So in any case, this method is widely used to investigate microstructure of materials. So on this screen you can see the typical picture, if you want, of the advanced scanning electron microscope Magellan 400. So let's a little bit talk about characteristics and so the physics of the method. Similar to the transmission electron microscopy, in the scanning electron microscopy we are using electron beam in order to investigate the material structure. However, so in this case, so we detected any kind of results of interaction of electrons with the surface of our material with detectors which are located on the same side with the initial electron beam. It's not transmission now, it's scanning. Scanning means that indeed, as in the TV screen, so we scan electron beam along the surface of the sample, grabbing information about this surface. So what kind of accelerations we are talking about in this case? They are not so high as in the case of TEM. However, they are on the order, still very high, on the order of 30 kiloelectron volts. And this electron beam coming on the surface of your sample, which should not be thin, any kind of samples with the size up to 10 centimeters can be put inside the scanning electron microscope. And so different kind of information can be obtained by the analysis of the results of interaction of this beam with the sample. So what kind of interaction we are talking in this case? So first of all, 2 modes of electron imaging. First of all, we can image backscattered electron. You can imagine that some number of electrons after interaction with the surface will be backscattered. And we have a special detector which detects these electrons, and we can get image in so-called backscattering mode. In addition, as the results of interaction of the initial beam, some new secondary electrons can be formed, and we have a special detector which detects these secondary electrons, so-called secondary electron mode or image. Similar as TEM, also the results of interaction of electrons with the surface of the sample, with the atoms in the sample, so the photons will be emitted. And in this case, we are using again energy dispersive spectroscopy analysis in order to provide to get information about the elemental composition of your sample. These 3 main modes we will talk about them in a little bit more details. So let's talk about let's say first about the secondary electron image. So secondary electron image, again, so the high energy incident electrons interacts with some volume, mainly surface of your sample, and the result of this interaction, some secondary electrons with relatively low energy actually, so are formed and detected by the special secondary detectors. As you can imagine, so the contrast of the image, secondary electron image, is due to the topography or morphology of your sample. So again, it means that if you want to get information about the size, shape of your let's say, particles, up to nanoparticles, or you want to see get information about the roughness of your surface, about the porosity on your surface, about the cracks on your surface. This imaging mode should be used. So again, it's this nice image of a bee, which provides you extremely nice resolution of any topographical, let's say, features of this biomaterial, if you wish. And again, the resolution in this mode can be as high as 1 nanometer, and then I will show you a little bit later. So I will prove this statement a little bit later. So again, a lot of information about the surface, topology, morphology, size can be obtained by using secondary electron image mode. So let's talk about resolution a little bit in more details. So remember, in the case of the TEM, we can get resolution as high as 1 angstrom. We cannot reach 1 angstrom resolution with the help of the scanning electron modes. However, so we can, in the typical, I want to say, advanced microscopes, we can get resolution below 1 nanometers. This screen illustrates you this idea. So you can see the typical sample, gold deposited on carbon. This is a special, of course, kind of sample which is widely used in order to define the highest resolution which can be reached with this microscope. And magnification of this image in the secondary electron image mode is 1 million, and the upper insert on this screen is up to 2 million. So, and the special software package exists which analyzes the quality, if you wish, of these images and gives you information about the reached resolution. In this specific case, you can see that the resolution on this Magellan 400 scanning electron microscope is on the order of 0.6 nanometers. That's extremely nice device which allows you to see not only microstructure if you want, but also analyze some level of nanostructured material. So many examples can be shown, and they're indeed beautiful, which demonstrate, let's say, the contrast and details which you can obtain on the very complex 3D surfaces with different level of magnification. Again, this screen demonstrates you this ability, and with different magnification, you can see with great details, with magnification now up to 3 million, so the typical features of this substance. Indeed, so for example, porosity here is less than, let's say, 20 nanometers for this special sample, and indeed in some cases 3D type even of imaging can be obtained. So with different magnification and with extremely high resolution. So on this slide you can see, for example, the catalyst. The catalyst, and then you supported catalyst. So on some oxide, on the some oxide surface, we have deposited some metal particles. And with different resolution, you can see not only the features of the surface, which was shown in the previous slide, but also the distribution of particles along these surfaces. So the other example is with this high resolution, you can investigate with the unique surface sensitivity, for example, carbon nanotubes. Again, so you can see the general length of these nanotubes, and increasing magnification, you can measure easily the diameter of these nanotubes, and then you can see even the features, again, some metal particles distributed along the surface of this tube. Let's conclude that if you want to get information about the surface, topological, morphological features of your material, you have to use so-called secondary electron image mode. So backscattered mode, a little bit different. And difference is that the main contrast on the backscattering images is due not to the topography, but is due to the difference in the atomic number of the elements of all of the phase which you have in your sample. So let's consider this statement with the help of the example. So we do have two SEM images of iron particles in carbon. So on the left, it is a secondary electron image, and it's not possible, I want to say, to resolve iron particle relative to the carbon. On the right, we have the backscattering mode, and you can easily see that the iron particles much more brighter as compared to the rest of the surface in this case, and you can easily identify these high Z particles on the low Z contrast. So it means that if you want to get information about the distribution of different phases with different average Z number, atomic number, you have to use backscattering mode. That's the other example. So in this cross section, and indeed in the backscattering mode, of course, it's better to use cross sections of your sample, because in order to neglect, not to account the topological effect. So if you have the cross section of your sample, you can easily see that here we, at least at this magnification, we do have at least 3 different phases. Lighter phase in backscattering mode, as you know now, corresponds to the phase with the highest average atomic number, and the darker one to the lower one. And we do have even intermediate, some gray phase here. So however, if we increase magnification, we can see then one more extremely dark phase also exists in this material. And this kind of analysis, especially when you combine it with the energy dispersive spectroscopy analysis, will give extremely powerful tool in order to define the phase distribution in your sample, even without using any kind of diffraction type of technique. So that's very specific feature of the backscattering mode. And other example is shown here again. So we have a cross section of material which involves aluminum and nickel. Nickel does have higher atomic number as compared to aluminum, as you can see. And with resolution, as I mentioned, on the order of 1 nanometer, you can see very nicely the distribution of nickel and aluminum phase in your material. Let's now move to the last possibility, last mode, or last kind of diagnostics which typically you have in your scanning electron microscope. I'm talking energy dispersive analysis of X-rays. So we have discussed briefly so what is going on here. So again, we have initial electron which somehow interact with the atom in the surface of in the volume of your sample, and as the result of interaction, so the ions, so one electron, let's say from the K level of inner structure emitted. As the result, we have ion in not, let's say, stable conditions. In order to go to the state with the low energy, electron from the M, let's say, shell moved to the K shell, and as the result, the photon with energy equals to the difference of energy between K and M shell will be emitted. And we have a special detector which actually detects this electron, and because the energy of this, and measure the energy of this electron, and energy of this electron, as you understand, strictly related to the electron structure of the element which we are investigating. So here, so what is important? Important to understand that actually interaction of the initial beam with your sample takes place in some volume. It means that you will obtain information from the volume of interaction, which depends, of course, on the accelerating voltage of your electron beam. So typically it's on the order from 1, I want to say, to 5 microns. So it means that so information about the elemental composition of your material you will obtain from this volume. So why it is so important to understand that? So indeed, if the size of your grains larger, let's say, than 5 microns, In this case, you will obtain information about elemental composition of this exact grain. But if the size of the grain is less than, let's say, 2 microns, in this case, information will be obtained from the larger volume and will correspond to the average, let's say, elemental composition of this volume, which may consist of many grains. And that you have to take into account when you provide the interpretation of the obtained results. So what can be, so in what form you can get these results? So this is a typical, let's say, distribution of peaks, energy peaks, which showed you the energy of the detected peaks and the number of photons which were grabbed with this corresponding energy. Of course, as we discussed already with you, so this energy is strictly related to the electron structure of this element, and that's why if you wish, the analyzing the integral under the obtained peaks, you can get information about percentage of this element, for example, of titanium, iron in this specific mica. The composition of this iron mica is very complex. It involves, as you can see, 1, 2, 3, 4, 5, 6 elements. So while you have to remember that EDS analysis doesn't allow us to detect very light elements. Such elements as hydrogen, such elements as lithium cannot be currently detected by EDS. So the whole analysis starts with the boron with Z equals to 5. So it means that if your sample, so if your phase consists or involves some kind of hydrogen, you have to account this by the recalculating of amount of hydrogen, starting assuming that you should have 100% of total elements in the investigated phase. From this standpoint, again, it is very useful to combine methods, for example, X-ray diffraction methods with EDS scanning electron microscopy method in order to easily recognize the phase of the phase distribution of the investigated materials. Indeed, in this case, you can get the so-called EDS mapping. You can, on the left side, you have the image, SEM image of your material obtained in the backscattering mode. You can see that you have at least 3 different phases here, and then on the right, so you have a representation of your sample obtained in the photons with energy corresponding to different elements, which provides you information about iron, magnesium, silicon distribution in your sample. Very useful approach. So let's conclude. So the typical scanning electron microscopy is very useful and very powerful tool to investigate morphology, secondary electron mode, and phase composition in some sense, backscattering mode, as well the elemental chemical composition of your material, EDS mode, so with resolution as low as 1 nanometer for the first 2 modes and around 1 micron for the EDS mode. However, before we make the final conclusion about this technique, I also want to mention a little bit about the new type of the scanning electron microscopy, so-called dual beam microscopy, where together with the electron column, with electron beam, which we have discussed just for the scanning electron microscopes, you also have an ion column. For example, the ion column, which also allows you to make images, but more important, it allows you to do something very special with the surface, on the surface of your sample. So what actually this dual beam Helios Nano Lab, for example, allows you to do? Many things. I want to put your attention on one, so which is related to so-called 3D reconstruction of the material. So typically, as we discussed before, you will make a cross-section of your material, stochastically distributed cross-section, and then investigate this cross-section. However, you understand that this is just one cross-section, and in many times it's very useful to know the distribution of elements, of phases, of features along the volume of your sample. How can you do this? So the trivial approach is to take your sample off from the microscope, make the other cross-section, let's say polishing 1 micron from the surface of your sample, put it back, make analysis again, and so on and so far. But it will take weeks or even months in order to obtain the desired information. What you can do in FIB, in focused ion beam, or in dual beam microscope. So you will use electron beam in order to investigate the structural characteristics of your sample. So however, you can use the ion beams in order to polish your sample just inside the microscope. Ion beam will take off up to 10 nanometers from the surface of your sample. Then you will use the electron beam to investigate the new obtained surface. And this operation can be repeated 1,000 times. And so on this slide, actually, you can see the movie, which doesn't have physical sense because it's not demonstrating you the changing of the phase distribution in your sample as a function of time, let's say at some temperature. So this is just images obtained slicing and viewing the surface of your sample. And in some sense, it demonstrates you the stack of images which you can get by using this so-called slice and view technology. And then by using 3D reconstruction software packages, you can reconstruct the 3D distribution of your elements. For example, titanium and aluminum in the shown on this screen example. And then you can make a different kind of cross-section in this 3D object and to see the distribution of these phases along the volume. Moreover, the other type of software allows you to analyze all characteristic features of each, let's say, phases. So thickness of the aluminum-based phases, volume ratio between the aluminum and titanium-based rich phases, the surface area contact between these phases, and so on and so forth. It is very powerful current advanced tool which allows you to know information not only about the surface microstructure, but also the microstructure along the volume of your sample. Just a few more information with the help of the same ion beam. You can make whatever you want on the surface of your sample. For example, you can make different type of channels. So with the thickness up to 10 nanometers or much more complicated structure, which you can see on the right of this screen. Moreover, you can even build the 3D articles on the surface of the sample. If you just design your article, it's on the left, the design in color is responsible for the height of each feature of this article, and then you incorporated this design inside the software tool of the focused ion beam. Then this ion beam with precision less than 1 nanometer will build or fabricate this type of article on the surface of your sample. So now we can conclude, and I hope that I convince you that a scanning electron microscope is extremely powerful tool to investigate the structural characteristics of your material on the micron and even nano level. And it has its advantages that the samples of different shape and dimensions can be used for this technique. So the only issue that which you have to have in your mind that EDS analysis in this case has resolution on the order of microns. I want to say so in the range from 1 to 5 micron. That's why the information obtained should have the right interpretation, taking into account that indeed information can be obtained not from the volume of one exact grains, but from the volume which involves several different type of phases. And also you have to account that light elements such as hydrogen and lithium cannot be detected, at least with the current type of EDS detectors. And so again, in this case, I can suggest you that to use combination of different techniques, specifically X-ray diffraction techniques and the EDS technique in the scanning electron microscope in order to obtain information about the phase distribution in your sample. Thank you very much for your attention.